Hello friends, welcome to my lecture on Brachistochrone problem and Euler's equations. We know that a necessary condition for the functional I equal to integral x1 to x2 fx y dash dx to be an extremum is that delta f over delta y minus d over dx delta f over delta y dash is equal to 0, and we call this equation as the Euler's equation. This problem which we are going to discuss now, this Brachistochrone problem, derives its name from the Greek words brachistos, and brachistos means shortest and chronos means time. So Brachistochrone problem actually discusses the shortest time that a particle will take in sliding down from one point to the other. This problem was proposed by John Bernoulli in 1696, and its solution formed the basis of the study of calculus of variations. Now here we shall find the path traversed by a particle which slides from a given point A to another point B in the shortest time under the action of gravity. We shall assume that the friction and resistance of the medium are ignored. So let us say the point A be at the origin. The y-axis is pointed downwards and this is our x-axis. So let A be the origin, y be measured downwards, and V be the point x1 by 1. Let us say this is the point x1 by 1. The particle slides down from the point A to the point B in time, let us say t. So then we assume that the particle starts sliding from the point A along the curve AB with the 0 velocity, and let us say take any arbitrary point P on its path. So the coordinates of P are, let us say, x, y, then y is this vertical height and this is x. So by the principle of conservation of energy, the kinetic energy at P will be equal to the minus kinetic energy at A will be equal to work done in moving the particle from A to P. Now if V is the velocity of the particle, then the kinetic energy at the point P, let us say the velocity of the particle Vv, so then half mv square minus, it starts at the point A with 0 velocity, so the kinetic energy there at the point A is 0, so minus 0 equal to mg y. Y is the height, vertical height of the point P. Now this B is equal to ds by dt. So what do we have? We can cancel m, and then we have ds by dt whole square equal to 2gy, or we can say ds by dt is equal to under root 2gy. Now let us say t is the time taken by the particle from sliding from A to the point B, whose coordinates we have taken as x1 by 1, then t will be a function of y, okay. Y will depend on x, and we shall have from here, if you take the square root, ds by dt will be equal to under root 2gy. We have taken a positive sign here because as t increases, s also increases. The arc AP is s. Now let us separate the variables. So we have dt equal to ds upon under root 2gy. When we integrate from 0 to from A equal to 0 to the point P, we shall have 0 to t yx will be equal to 0 to x1, and then ds is equal to under root 1 plus dy by dx whole square into dx divided by under root 2g by, or we can write it as so we can write t by x equal to 1 over root 2g is a constant, we can take it outside the integral. So 1 over root 2g integral 0 to x1 under root 1 plus y dash square over root y, and let us now assume that fx by y dash be equal to under root 1 plus y dash square over root y. So let us say one over root 2g is a constant, so it does not play any role in determining the extremum value of this integral, so we have taken it outside. And now let us recall that if the function fx by y dash is independent of x, then the Euler's equation is given by this alternate form. The Euler's equation reduces to d over dx f minus y dash delta f over delta y dash is equal to 0. So here you can see that fx by y dash depends only on y and y dash, it does not depend on x, so the Euler's equation reduces to this. And the proof of this is a alternate form of, we can easily do this. Alternate form of we have the Euler's equation as this is the Euler's equation. Now let us find its alternate form. Let us find first d over dx of f. Now f is a function of x by and by dash, so I can write it as delta f by delta x delta f by delta y into dy by dx plus delta f by delta y dash dy dash by dx, or I can write it as like this. And then let us find d over dx of y dash into partial derivative of f with respect to y dash. Then what we will get? Y dash times d over dx of plus into y double dash. Let us call this as equation 1 and this as equation 2. So when you subtract the equation 2 from 1, so subtracting two from 1, we have df by dx minus d over dx of y dash delta f by delta y dash. Now what will happen when we subtract 2 from 1? This term delta f by delta y dash by double dash will cancel with delta f over delta y dash by double dash, and what we will get? Delta f by delta x plus delta f by delta y minus d over dx of delta f by delta y dash into y dash, or we can say I can write it as d over dx of f minus y dash delta f by delta y dash, that is the left hand side, minus delta f by delta x equal to delta f by delta y minus d over dx of delta f by delta y dash into y dash. Now from the Euler's equation we know that this is 0, delta f by delta y minus d over dx delta f over delta y dash is equal to 0, so right hand side is equal to 0, and thus we get the r, I can say d over dx of f minus y dash delta f by delta y dash minus delta f by delta x equal to 0. So this is another form of the Euler's equation, and in case f is independent of x, it reduces to d over dx f minus y dash delta f over delta y dash equal to 0. Like here f is a function of y and y dash only, it does not depend on x. So the Euler's equation, this one reduces to this equation. Now from here when we integrate with respect to x, we will have f minus y dash delta f over delta y dash is equal to some constant. So this is what we have, f minus y dash delta f over delta y dash is equal to c. Now f is equal to, let us simplify this equation. F minus y dash we have f equal to under root 1 plus y dash square upon root y. So we find the partial derivative with respect to y dash from here. So we shall have 1 over root y 1 over 2 square root under root 1 plus y dash square into 2y dash. So this 2 will cancel with this 2 here, and then f minus y dash delta f over delta y dash is equal to c gives us under root 1 plus y dash square divided by root y minus y dash times y dash divided by root y into under root 1 plus y dash square equal to c. So what we will get, root y into square root 1 plus y dash square, and then we shall have 1 plus y dash square minus y dash square equal to c. So this cancels and we get r under root y into under root 1 plus y dash square equal to 1 by c. So what we get is we can solve it. So let us see, this is y times 1 plus dy by dx whole square 1 over c, if we put as c1, so then this is c1, so r we can say dy by dx is equal to c1 over y minus 1 square root. Now as x increases, y also increases, so we get this, so c1, this is, so separating the variables we will get r root by over c1 minus by into dy is equal to dx. Let us integrate with respect to let us integrate both sides. So integral this will give you integral 0 to x dx equal to integral 0 to x So let us now let by be equal to c1 sin square theta. So left hand side becomes x and we get here 0 to dy will become 2c1 sin theta cos theta d theta, and this is when x is x, by is by, so I think we should put here by here. So this will give you 0 to pi by 2 and or we can say 0 to theta, not pi by 2. At this point 0, it should be theta, not 0, not pi by 2, it should be theta. So this is x here, let me write x here. So this is c1 sin square theta, and what we will get c1 minus c1 sin square theta is c1 cos square theta, dy is 2c1 sin theta cos theta d theta. We have to put the limits for theta, so we have written it theta. So this is c1 cancel out here, and what we will get here 2c1 integral 0 to theta, and then we shall have cos theta will cancel with cos theta, we shall have sin square theta d theta. So what we have is this. So this is, now we can integrate this. So this is x equal to c1 times 0 to theta and then 1 minus cos 2 theta d theta. So this is equal to c1, then we have theta minus sin 2 theta by 2, the integral of 1 minus cos 2 theta. So 0 to theta will give you c1 by 2 theta minus sin 2 theta. Now let us say let c1 by 2 equal to a and phi b equal to 2 theta, then x is equal to a times phi minus sin phi, and by is equal to c1 sin square theta. So by is equal to c1 is equal to 2a, and sin square theta is 1 minus cos 2 theta divided by 2. So this will be a times 1 minus cos phi. So x equal to a times phi minus sin phi, y equal to a times 1 minus cos phi, and it is very well known that the parametric equations of the cycloid are given by x equal to a times phi minus sin phi, y equal to a times 1 minus cos phi. So when the particle slides under the action of gravity, where the resistance and the friction of the medium are neglected, it travels along a cycloid. Its path is that of a cycloid. The constant here is determined from the fact that the particle passes through the point x1 by 1. So that will give you the values of a and phi. Now so the path of the particle is a cycloid. Now let us consider Euler's equation in the case of several dependent variables. You have earlier done the Euler's equation in the case of one dependent variable. Now we shall be doing the Euler's equation in the case of several dependent variables. So in previous lectures you have studied how to find the extremum value of this functional, where there is one independent variable x and there is one dependent variable y. So we discussed the case of the Euler's equation in the case of one dependent variable. Now we shall extend the study to the case of several dependent variables. So the rational problem will be now extended to the case of several variables as function of a single independent variable. Let us consider, for example, this functional integral x1 to x2 f x by 1 by 2 yn by 1 dash by 2 dash by n dash dx, this functional. We want to extremize this functional where yi's are dependent variables which all depend on the one single independent variable x, and I varies from 1 to n. So there are n dependent variables all depending on one single independent variable x, and the condition for this functional to be an extremum is that the partial derivative of f with respect to yi is ith dependent variable, minus d over dx partial derivative of f with respect to yi dash is equal to 0, and this must hold for all values of I equal to 1 to n. So there will be a system of n equations here corresponding to the n dependent variables by I. Now we shall prove this result. We shall find this necessary condition for this functional for the case n equal to 2. The proof can be easily extended to the case of any arbitrary n. Now let us consider the functional I equal to x1 to x2 fx by 1 by 2 by 1 dash by 2 dash. Now we wish to find the necessary condition to be satisfied by the two functions by 1 and by 2 which depend on a single independent variable x, and those values of by 1 by 2 which extremize this functional I. So let us suppose that by 1 and by 2 x satisfy the boundary conditions at the point x1 by 1 x1 is equal to by 1 1, and by 1 at x2 is takes the value by 1 2, by 2 function at x1 takes the value by 2 1, and by 2 at x2 takes the value by 2 2. Let us consider two arbitrary functions eta 1 x and eta 2 x which assume value 0 at the boundary points. Eta 1 at x1 and eta 1 at x2 is equal to 0. Similarly, eta 2 at x1 and eta 2 at x2 is equal to 0. Now what we will do is, in the given functional we shall replace by 1 and by 2 by 1 plus epsilon 1 eta 1 and by 2 by 2 plus epsilon 2 eta 2. Then the functional that we get will be a function of epsilon 1 and epsilon 2. We shall call it as I epsilon 1 epsilon 2. So the functional will take the form x1 to x2 fx by 1 plus epsilon 1 eta 1 by 2 plus epsilon 2 eta 2, and then by 1 dash plus epsilon 1 eta 1 dash by 2 dash epsilon 2 eta 2 dash. Now this I then is a function of two parameters epsilon 1 and epsilon 2, and you can see that it reduces to the previous given functional this one when epsilon 1 and epsilon 2 take value zeros. Now to find the stationary value of this function, since I is a function of two variables epsilon 1 and epsilon 2, it will assume extremum value provided its partial derivatives with respect to epsilon 1 and epsilon 2 are 0. That is, those are the necessary conditions for I epsilon 1 epsilon 2 to have an extremum value. Now when we differentiate I with respect to epsilon 1, let us see what we get. So this is I. When we differentiate it with respect to x, with respect to epsilon 1, since the integrand is a function of I1 epsilon 1, so we will have to use the Leibniz rule of differentiation under the integral sign, and here the limits of integration are constant. So we shall have x1 to x2. Now let us say that by 1 bar be equal to by 1 plus epsilon 1 eta 1 and by 2 bar be equal to by 2 plus epsilon 2 eta 2. Okay, then since the limits of integration do not depend on x1 and x2 upon epsilon 1 and epsilon 2, the partial derivative of y with respect to epsilon 1 will be x1 to x2, the partial derivative of this integrand with respect to epsilon 1. And when we differentiate it with respect to epsilon 1, we shall have so delta f over delta by bar, delta by bar by 1 bar and delta by 1 bar over delta by 1 bar over delta epsilon 1 will be equal to eta 1. So we shall have eta 1 and then delta by 1 f over delta by 1 bar dash into epsilon 1 dash. So when we differentiate it partially with respect to epsilon 1, this will be differentiated with respect to epsilon 1. This is by 1 bar, this is by 1 bar dash. So partial derivative of f with respect to by 1 bar into partial derivative of by 1 bar with respect to epsilon 1, which is eta 1, partial derivative of f with respect to by 1 bar dash. So this is this, and then partial derivative by 1 bar dash with respect to epsilon 1 will be eta 1 dash dx. So this is what we have. Now we have delta I over delta epsilon 1 is equal to 0 when epsilon 1 is equal to epsilon 2 equal to 0. So when epsilon 1 and epsilon 2 are zeros, by 1 bar becomes by 1 and by 1 bar dash becomes by 1 dash, and hence we have integral x1 to x2 delta f over delta by 1 eta 1 plus delta f over delta y1 dash eta 1 dash dx equal to 0. So we have this equation, integral x1 to x2 delta f over delta by 1 eta 1 plus delta f over delta by 1 dash eta 1 dash dx equal to 0. Now let us integrate by parts the second term of this on the left hand side. So when we so let us see integral x1 to x2 delta f over delta by 1 dash eta 1 dash dx. When we integrate it by parts, we have the partial derivative of f with respect to by 1 dash into eta 1 x x1 to x2 minus x1 to x2 d over dx of this. Now we have assumed that eta 1 vanishes at x1 and x2. So since eta 1 x2 is equal to 0, eta 1 x1 is equal to 0, so we shall have 0 minus integral x1 to x2 and d over dx of so the second integral here, second term here becomes this. So this gives us r x1 to x2 delta f over delta y1 eta 1 minus d over dx of we get this. Okay, so thus we have integral x1 to x2 delta f over delta y1 minus d over dx delta f over delta y1 dash multiplied by the function eta 1x dx equal to 0. Since this equation holds true for all choices of eta 1x, Therefore, we must have delta f over delta y1 minus d over dx of delta f over delta y1 dash equal to 0. Similarly, when we differentiate I epsilon 1 epsilon 2 with respect to epsilon 2 by using the Leibniz rule of differentiation under integral sign and put epsilon 1 epsilon 2 equal to 0, what we will get is delta f over delta by 2 minus d over dx of delta f over delta by 2 dash equal to 0. And thus to find the extremals of our problem, we solve the two equations. This is this equation and this equation. So corresponding to two dependent variables by 1 and by 2 which depend on x, we have two equations here which are to be solved. So these two equations we have to solve to find the extremal of the problem in the case when n is equal to 2. In the general case, we can generalize it to n variables. So in the case of n variables, when I is integral x1 to x2 fx by 1 by 2 by n by 1 dash by 2 dash by n dash dx, then similarly we can say we shall have to solve n equations. Delta f over delta yi minus d over dx delta f over delta yi dash equal to 0, where I runs from 1 to n, 1, 2, 3 and so on up to n. In our next lecture, we shall take examples on this Euler's equation in the when the number of dependent variables are several and they depend on a single independent variable. So with this I would like to conclude my lecture. Thank you very much for your attention.